This lecture is on finite state machines. The idea with a finite state machine is to get your electronics to behave like something in the real world would. And the main challenge is to get the electronics to not behave in the same way every time. The behavior of your electronics will depend on what state the electronics is in. The example that I use to explain state machines is typically that of a baby. So if you consider what I've done at the top here, I've made a simple baby, and I've given three states to this baby. I've given a state of sleeping, a state of awake and livid, a state of awake and happy. And what you can see is in between these three states, a baby can transition depending on what inputs you give it. So, for example, if the baby is awake and happy and you sing to it, it will go into a sleeping state. If the baby is sleeping and there's a hunger input, so it detects hungry, then it will go into the awake and livid state. If it's awake and happy and it becomes hungry, it will go into the awake and livid state. And if it's in that awake and livid state and you add milk, you give it milk, then it becomes awake and happy again. Very simple. But what you should take from this is that there are different states that this baby can be in, and there are inputs that changes how this baby behaves, essentially meaning that the output will be different depending on what state the baby is in. So three separate things: the inputs, the present state, and then also what output you will have in each state. So the outputs are listed here. If the baby is sleeping, so if the present state of the baby is sleeping, the output will be snoring or deep breathing. If it's in a state of awake and livid, the output will be screaming. And if it's in a state of awake and happy, the output will be laughter. So what is drawn at the bottom here is the typical architecture of a state machine. And we call it a finite state machine because it has a finite number of states. In Afrikaans, we call it a toestandsmachine. So on the left-hand side here, we can see that we have some inputs, and one of the inputs into this thing here, which determines what will be the next state, is the present state. So the present state, as well as the inputs, they determine what the next state will be. Then we also use memory here to remember what state we're in, and we use some block again to determine what the output will be, and this depends on the present state. So what you will see is this input block, or this what we call the next state logic, that determines what the next state should be. That's just going to be normal AND gates, OR gates, and NOT gates, just normal combinational logic. On the output side, again, this thing that determines what the output will just be combinational logic. However, the middle part, this is the part that remembers what the present state is. It's like the inertia of any system in the real world. It remembers what state you're in. Just as you as a human, you remember what state you're in. If you're in a state of tiredness or in a state of being awake, you have that built into your system. In order to emulate that using electronics, we use memory. And the only memory device that we really know that we can use is a flip-flop. And that just brings me to the final point on this, or the second last point actually, is that we need to sample this at a certain time. And this, you should realize, is the clock that drives the flip-flops. So the flip-flops will remember the state, and then the clock will tell the flip-flop when does it need to check if it needs to transition to a different state. And this block of logic tells it what that next state would be. And the final point on this is just because we have three states, the states are sleeping, awake and livid, awake and happy, you can see that in electronics we can't really do labels. We can't remember labels. So the way that we remember stuff is, or the way that we categorize stuff is, we enumerate them. So the sleeping state we've enumerated as 0, 0, awake and livid state we've enumerated as 0, 1, and the awake and happy state I've made 1, 0. Three states require 2 bits, so there's one state that we don't use, the state 1, 1, we don't use. This is important, you'll see now, because that next state signal there is really going to be the number of lines that represent the number of bits that we have to use to save the state. Same here, present state or current state will also be 2 bits, which implies that we'll have to have 2 flip-flops to remember what state we're in. Remember, 1 flip-flop remembers 1 bit, and the next state logic will have 2 outputs, and then this output logic will have 2 inputs to determine what the output should be. So what you can see here is just the generic framework. It's very similar to the baby example, but what you can see is we have inputs W, and then we have a combinational circuit, some block of logic, that looks at that W. It also looks at what the present state is, presents out into the flip-flops what the next state should be when there is a clock edge, and the flip-flops just tells you what is the present state. The output depends on the present state. It is also possible to have your output dependent on the present input, and if that's the case, you can see there's a dotted line there. That dotted line represents a mealy state machine. If it's not there, which it won't be for this module, we call it a Moore state machine. So a Moore state machine says the output is only dependent on the present state, it doesn't depend on the inputs directly. And that's what's listed here. Moore state machine, Mealy state machine. Okay, so the easiest way to look at these state machine concepts is really through an example. So the example that we're going to do is we're going to develop circuitry to perform a sequence detection. And the sequence that we're going to have to detect is a sequence of 2 ones. So in this slide here, you can see an example of what the circuit's supposed to do. If it detects for 2 clock edges, just be careful. The textbook uses the word clock cycles. That should really be clock edges. It implies more or less the same, but it's a bit of a subtle difference. If it has detected 2 ones on the input, subsequent ones, then the output should be a 1. Same here, if it detects 2 ones on the input, then the output should be 1, and the same here, if it detects 2 ones on the output, on the input, the output should be 1. So sequence detectors is something that we do with state machines. You can also use a shift register, but that's not what we're going to do. We're going to use state machines because we want to demonstrate state machines. So please don't get confused with shift registers, which is something that remembers the input, with a state machine, which is something that remembers a state. Quite a substantial difference there. Alright, so the first thing we need to do is we need to decide how many states do we have. That's the first thing you do when you get a state machine. You need to ask how many states do I need to capture what the question says. And what I typically do is I just define one state as my entry state. It's typically called an idle state. What do we want to do is we want to say we need a state to say we've not received anything. In the sequence that we have, we've not received anything. Or another way to look at it is to say our circuit has just been reset. It's like the reset state. And I don't mean it's being reset. I mean it has been reset. Okay, so that's the first state that we enter into. Let's just label it A. So we've not received anything. Then what I typically do is I say let's follow the normal sequence and see how many states we have. So state A is we've received nothing. State B is we've received a 1, or there was a 1 at the input. State C is we've received yet another 1. So in this case we've received another 1. We transition into what I have here, what I've called state C. So I've received nothing, I've received 1 1, or seen 1 1 at the input, and then I've seen 1 1 at the input as well. And a very important thing to understand here is these state transitions occur on the clock edges. If you just go back to this block diagram, you can see the next state is clocked through into the present state when there's a clock edge. That's how flip-flops work. Flip-flop says if there's a clock edge, copy this side, paste it on this side. This is how it works. So these transitions, it's implied, it's never written down. These transitions happen on clock edges. This is the input, it was there on a clock edge, so it transitions. So in this state A, we receive a 1, or the input is 1, it goes to state B, it goes to state C if it's 2 1s. However, if I'm in state B and I receive a 0, I go back to A. If I'm in state A and I receive, or I have an input of 0, I go back into state A. And then if I'm in state C and I receive a 0, again, W is equal to 0, it goes back to state A. So that should cover all the possible transitions. There's one more. State C, if I receive another 1, it means I've received 3 1s, so I again have a sequence of 2 1s, which keeps me in state C. I wanted to say something about that. Oh yes, you will see sometimes people leave one of these out. So if it stays in the same state, they just leave out this transition. They just leave out this, which implies it won't move, because it implies that it'll only go out of state C if W is equal to 0. So this is really implied when you leave it out. But let's put it in for completeness sake. In state A, I've received nothing, so my output is equal to 0. We list the outputs in that state. Output is equal to 0 in state B. And then in state C, I've received 2 1s, so my output is equal to 1. Just redo that quickly. Z is equal to 1. Okay, so that brings me to the next step in this design sequence, and I can guarantee that this will be the difficult part. This state machine that we've just done, that's the difficult part. When you've done that, the rest is really fairly easy. All we need to do now is we need to make a state table, and before that I just want to explain what we're doing yet again, just so that you get the bigger picture. The bigger picture of what we're doing is we want to design the logic that performs this function, we want to design the logic that performs this function, and we want to put in flip-flops to remember the state. So as I said, the first thing you need to ask yourself is how many states. That'll tell you how many flip-flops. Then what we've done is we've drawn this diagram here, which tells you how it will transition between states. And all we need to do now is we need to make a truth table to say, given certain inputs, what should the output be? Just a normal truth table. On this side the same. Given certain inputs, what should the output be? Just a truth table. So try to keep that in mind. We want to progress towards a truth table. So if you look at this state machine and we make a truth table for it, the way we do it is we use a state table. And the state table says, given my present state and given my input, what will my next state be? You can see this starts to look more or less like a truth table. And then also, what will my output be? So given my present state, which would be I, A, B, or C, those are the only states we have, what is my next state? And that will depend on what the input is. If the input is 0, I transition to state A from A. If it's a 1, I transition to B. If I'm in state B and I have an input of 0, I transition to state A. And if it's a 1, I transition to state C. If I'm in state C and I receive a 0, I go back to A. And if I'm in state C and I receive a 1, I stay in C. And then the other thing we need to do is we need to just say, what will the output values be? So the output, and this is important to just grasp quickly, the output depends on the present state, not on the next state. So many people get this wrong and get confused. The output depends on the present state, not the next state. So your present state, if I'm in state A, the output is 0, state B, the output is 0, state C, the output is 1. So all we're going to do now is we're going to convert this into a truth table. So the thing that's lacking, and if you forgive me, I'm going to try to squeeze it in here. All that's lacking to make this thing a truth table is we need numbers. This is essentially a truth table capturing many of the options, we just want to put numbers next to it. So what we do is we enumerate the states. And when we do that, we call it a state assigned table. So I'm going to do the same thing here, just in less space. So present state, next state, input, input, and output. I'm just going to add a line as well so that we can do bits. So what we do is we say, let's make state A state 0, 0, which is quite convenient because this reset here we will connect that to the reset of the flip-flops or the clear of the flip-flops, which will make the state 0, 0. So let's make A 0, 0. Let's make B 0, 1, C 1, 0, and then we also have the state 1, 1, which would have been D, but we don't use it. So and then all you do is you use these numbers and replace them in the tables. So 0, 0, 0, 1, 1, 0, 1, 1. If the input is 0, well, I'm not going to repeat what the thought exercise. Let's just complete the table. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0. And then the interesting thing, what happens here is, because this state doesn't exist, we can just say we don't care. We don't care. We don't care what those are. We don't care what the output is. We shouldn't ever enter into this state. Just be careful. Typically, if you work with safety systems, you don't want to use don't care. With a safety critical system, you want to say, if it enters this state, my circuitry is broken, which means let's return to a known state 0, 0. So this don't care is very convenient for us now. But if you go and design Boeing aircraft or something like that, you don't want to use don't cares. The output, as we said, is 0, 0, and 1 right there. So this is our state assigned table. This is our state table. And what I want you to realize now is this here is just a truth table, where my present state is made up of 2 bits. So I just want to get the way that the example did it. Present state, we use lowercase y2 and y1. Next state, uppercase y2, y1, uppercase y2, y1, and then z is just that. So you can see the truth table is, these are my inputs as well as w into a block of logic. So if this is the block of logic that tells me what my next state would be, w is an input, lowercase y1 and y2 are inputs, and my outputs are uppercase y1 and y2. So all I do now is, and please go through the motions here, I know it's boring, but you're going to make mistakes if you do it in your head. So all I need to do is I need to convert this into a proper truth table now, and that I can do fairly easily. Y2, y1, as well as my input w. Write down all the possible combinations, or just go through the motions. So 0, 0, 0, did you get that? 0, 0, 0 leads to a 0 and a 0. 0, 0, 1. So if I'm in state A and I get an input of 1, my next state is 0, 1. So I'm doing exactly the same thing here. I'm just rewriting the table as a truth table. If I'm in state B and I receive a 0, I need to go to state A. Or the other way to do it is 0, 1, 0 leads to 0, 0. And in the same way, you can complete this whole table just by rewriting this into a normal truth table. 1, 0, 0, I'm just going to do this quickly. 1, 1, 1. So of course the 2 states that I don't have, so this is state D, this is state C, and this is state B, and this is state A, and this is the input in each of it. If I'm in state C and I receive a 0, I need to go to state A. If I'm in state C and I receive a 1, I need to go back into state C, or just stay in state C for that matter. So all that I need to do is I need to just convert this into Kano maps and then determine what the logic looks like. I forgot about the output, so let's just do the output. You can see for state A, my output is Z is 0. For state B, my output Z is 0. For state C, it's 1. And for state D is D, I don't care. So what you do now is you say, let's calculate Y2, so the most significant bit of my next state. It's dependent on lowercase y2, uppercase y2, and w. Zero, 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 1, 1, 1, 1, 0, and a 0 and a 1. There we go. Uppercase y2 is 1 for 0, 1, 1, so 0, 1, 1. It's also a 1 for 101, 101, and then it's a don't care for state D. So you can see this is essentially state D, this is essentially state A, state B, state C. Just to keep track of what we're doing. That's essentially what we're doing. In state D, it don't cares. So what you can do is you can group those together like that, leading you to an expression y2 is equal to w y2 plus w y1, if I'm not making a mistake. Yeah, that's about right. And then you can do the same thing for uppercase y1. Just do the same thing. You can see it only has 1 1 there. Let's do it. Y2, Y1, and W. There's only 1 1, and that's at 0 0 1, 0 0 1. There we go. And then the rest is D's over there. We don't need to use the D's. We can just use this single term here. So Y1 is just equal to, I'm just going to flip to the slides to see if I've made a mistake. No, it's about right. So Y1 is just equal to not Y2, not Y1, W. And then you do the same thing with Z. So Z is a bit simpler because it only depends on Y2, Y1, because we have a Moore state machine. 0, 1, so it's a bit silly to do this, but let's do it. So for state D, the output is just D, we don't care. And for state C, the output is 1. And state C is 1, 0. So if you group those together, then Z is just equal to Y2. So that means you can draw this diagram out, and it looks something like this. That's what we've just designed. We've just designed a circuit that will perform this function. Important thing to understand, yet again, is your flip-flops transition from what the logic should say the next state is. I'm going to say that again. The flip-flops make that state transition to what this block of logic, the next state logic, says the next state should be when there's a clock edge. And the output is just dependent on your present state. So let's look at this quickly. This here is your timing diagram, and I have to say, if you understand this, you can tick off state machines, then you know that you understand what's going on. So first of all, let's assume that we're starting with the state 0, so we're in present state 0, 0. And then we have clock transitions, rising edge, rising edge, rising edge, rising edge, and those are when W is sampled. And actually that's when the next state is sampled, I should say. So the next state is dependent on these three inputs. So let's quickly look at that. For the first rising edge, I'm in state A, the input is 0, so it just stays in state A. Then I have another rising edge here. So in this rising edge, or at this rising edge, input is 0, I'm in state A, so it stays at 0. Then my input, which is driven from somewhere outside, okay, somebody has control of this, we don't have control, we just receive it as is. Then input W is equal to 1 at the next rising edge, so because it's 1, my next state logic says you need to go into state B. That's what the next state logic says, because I'm in state A. And you will see a few nanoseconds later, the transition happens. The nanoseconds delay is just because the flip-flops take a few nanoseconds to perform this action. So rising edge samples W, a few nanoseconds later I'm in state 0, 1, which is state B. On the next rising edge, W is equal to 0, so a few nanoseconds later, yep, indeed, you can see that Y1 changes to 0 again, I'm in state A again. Next rising edge here, sample W is equal to 1. Because it's 1, it goes back to state B. 0, 1, you can see a few nanoseconds after the rising edge. On the next rising edge, it's still 1, so it transitions from state 0, 1 into state 1, 0, so it goes from B into C. And then what you should see is, as soon as that happens, Z goes to 1, because, just going back to our diagram, Z is just connected to Y2. So for completeness sake, good exercise would be to just redraw this whole clock diagram on a piece of paper with the capital Y1 and capital Y2 in between here to understand what's going on. If you do that, you should see that these transitions happen as they're described here. And that's really the gist of state machines.